Welcome to the third video on the free and open source GODOT game engine platformer series. In this video, we will continue with the same 2D platformer example that we have been developing in different game engines. We will implement the attack and damage functions on the player, and we will adapt it to work with finite machine states, as to make it easier to work in the future with it. Let's dive into GODOT. Okay. Before actually starting with the new systems, we actually need to solve a small problem that we have left from the previous video. If we look closely at the skeleton enemy, we can see that the character is somewhat blurred when compared with the player. This is because we have forgotten to, when importing, to remove the filtering that GODOT applies to the textures. Let's fix it. For that, let's locate in the resources hierarchy, the sprites we used for the enemy. At the top of the hierarchy pane, click on the Import tab. If you look for the filter propriety, you can see that it is active. So, in the resources pane, select all the enemy sprites, and then click on the filter option to switch it off. Then, click on the re-import button and you will see that GODOT starts re-importing all the assets. As soon as it finished, you can see that now the skeleton enemy in the scene view is no longer blurred. Let's now implement the player's hitbox and enemy damage function, just like we did in the previous episode for the skeleton's enemy. So, in the hierarchy pane select the player, and then click on the add icon in the hierarchy header. In the search bar of the Create Node UI, type in area, and select it from the node list. Click on the Create button to finish the process. Repeat the process to create a collision shape 2D. Make sure it is created as a child node of the area 2D. In the right inspector pane, under the drop-down menu shape, select the option New Rectangle Shape 2D. In the game window, resize it and place it in the front of the player where the sword will move through when performing the attack. In the inspector pane, click the option Disable to disable it, as we want it only to be enabled a couple of frames during the attack. Next, in the hierarchy, click on the area 2D, and in the inspector pane select the collision option. Set the area 2D to be on the player layer, and the mask to be against the enemy's layer. Later on, if we need the player to break chests or other destructible props, we will add more elements to the mask. Let's rename the collision shape to be named Hitbox by either right-clicking on it and choosing the rename option from the menu, or by double-clicking on the node and editing the name directly in the hierarchy. Once done, let's connect its signals to the player script, as to receive the input when an object has been detected inside the trigger area. Select the Area 2D object and then in the inspector pane, select the Node tab. From the list, select the option Body Enter, and then click on the button Connect at the bottom of the pane. In the pop-up window, make sure the player is selected and then click on the button Connect. We are taken back to the new code that was generated by GODOT. Since we have already implemented this code for the enemy, let's copy it and add it to the function. Since we do not have a weapon damage variable, GODOT is complaining about an error, so let's go to the top of the player script and let's add the weapon damage variable. In our case, we are going to set the initial value to 10. Now, we need to do the inverse action regarding the take damage function as the enemy has not yet that function that would allow it to receive any damage. Let's make some adjustments to adapt it correctly to the enemy. Replace the player life with enemy life. And let's create the variable at the top of the enemy script, and let's set its initial value to 50. Let's create also the variable as hit, that will hold the condition associated with being hit, and that will allow us to control the flow of the hit function. In the player script, under the animation finished function, select the code that we have added in the previous tutorial. We need to finish the reset of the is hit to false when the animation has finished playing. Select the animated sprite for the enemy skeleton, and then, in the inspector panel, under the node tab, create a new signal function associated with the animation. Paste the copied code and adjust the if statements. Time to implement the attack function on the player. Locate the code where we are checking for the inputs, and let's add a new input check on if we are pressing a button. For now, we will leave it empty, but we will come back to it in 1 minute. If the button has been pressed, let's record that we are attacking through a variable is attacking that we are setting to true. Then let's play the attack animation. Let's go to the top of the script, and let's define is attacking with an initial value of false, as we are not attacking. Let's go back to the inputs, and, in the string for the input action, let's type in enter, as we will be using it to perform the attacks. Run the game to see if it works. And? Nope. The attack animation is not played. Go back to the code. Let's replace the is action pressed instruction with is key pressed. Replace also the enter with key X. Let's also change the location of the code to be above the if condition where we are testing if the character is not being hit. Copy it, and move it to be above the condition. We have also a typo on the animated sprite name, it is written with a small cap when it should be with a capital. Let's run the game. And? The attack animation is being played correctly. But this is just the animation being played. Behind it, there isn't yet anything. Let's implement the attack function for the player. So, in the physics process, let's invoke it. And then, right below, let's define the function. Go to the enemy skeleton script, and copy the attack code that we have implemented in the previous tutorial. Paste it under the player attack function. Let's delete the player in range condition, as it does not apply to the player attack. Rename the attack animation name for the player. Delete the else statement, the associated code. Let's make some optimizations. Up to now we have been accessing the animated sprite by referencing it with the $sign in front. This is equivalent to continuously making a get node to access it. Let's cache it at the beginning of the script. Let's replicate the process for the HitBox reference, that we will have to access several times too, using getNode function. And passing as parameter area2d/hitbox. Let's change all the references from $animated sprite to only animated sprite. This will save a lot of computing cycles. In the attack function, let's enable the hitbox by setting the disabled propriety to false. We can do this because the attack animation of the player is very short, only a couple of frames. If the animation was longer, then we would need to replicate the process that we have used for the enemy attack animation, and wait for the correct frame where to enable it. Let's go to the animation finished signal function. Let's first fix a reference to the animated sprite that we have missed, and then, let's copy the code for the hit animation and paste it below. If the player was playing the attack animation, then let's disable the hitbox by setting the disabled propriety to true. Finally, let's change the animation back to idle too. Let's run the game. Okay. We have a small problem, we are always performing an attack. Let's fix it. Go to the attack animation and in the first if statement, let's add the condition that the player is not attacking. For that, we will check the value of his attacking and invert it, by using the exclamation mark in front of it. This will make sure that we will only enter the instructions associated with attacking, if we have just pressed the attack button. Let's run the game. Now, it is performing the attack correctly when the attack button is pressed, but it is continuing to attack forever. Move the attack function into the if statement where we are checking if the X or attack key is pressed. If we run the game, we still have a small problem, as when the enemy is getting hit, it is still trying to attack us. Let's quickly fix it. In the attack function of the enemy, let's add an if statement, where we check if the enemy skeleton is being hit, in this case, return don't run the attack code. Let's run the game. We can attack the enemy, and while being hit, he is not able to attack us back. But we are missing a lot of different features, like effects, knockbacks, chained attacks, combos, etc. What is the problem? That the solution we have been implementing up to now is simple for a couple of simple attacks and hit behaviors, but if we wanted, for example, to add a knockback effect on the player or enemy when being hit, it would be very difficult to manage the changes and would demand a lot of code to implement. At the same time, this blend of complexity and growing lines of code would be the perfect place to generate a lot of bugs. This means that if we need to make some changes to the code before we lose control of it. How? The answers are at the same time easy and difficult. There are a lot of different systems that we could be using and different ways that we could implement them, but we will go through the usage of finite state machines. A finite state machine, FSM, in a more technical term, is a mathematical model of computation where an abstract machine can be in only one of a finite number of states at any given time. The changes between states are perfectly defined by entry and exit conditions that guarantee that the next state from one state is also easily defined. Some examples of machine states could be, for example, a door. The door can be closed or can be opened. But it cannot be opened and closed at the same time. In the case of video games, a simple character can be in idle, walk, and run states. We can go from the idle to the walk state, and then, from the walk into the run. But we cannot go from the idle directly into the run state, because the state machine will not allow it. We can go from the idle state to the walk state when our velocity is bigger than 0 meters per second. We can also go from the walk state into the run if the velocity is greater than 3 meters per second. Let's see an example with the jack-lantern character that we have downloaded from the internet. The link will be on the description. If the character velocity is 0 meters per second, the character will stay in the idle state and display the idle animation. If the speed increases to 2, then the condition between the idle and walk state will be true, and the state machine will move the focus into the walk state, and the character will change its animation to the walk. While the speed is not increasing or decreasing, the character will stay on this state. If the speed increases to 4 meters per second, then the state machine will move to the run state and the character will start to play the run animation. We cannot go from run to idle, because the system would not allow it, and we would have to go back through the walk state. How can we implement finite machine states in Godot? We have several ways: by getting a plugin from the store, by implementing machine states with classes, or implementing them via match cases. The first one doesn't make sense, because then we wouldn't learn anything. The second one is usually very complex to understand the concepts of machine states and how they simplify the coding of complex and interrelated mechanics. The third one, although not the purest way to do it, is the one that allows understanding exactly how they work and is required to implement one. So, we will implement the finite state machine in this way. Let's start because we have a lot of work to do. Since we are working on our player character, we will apply the state machine to the player. First, we need to define the states that the player will have. We have identified idle, walk, jump, attack, chirp, and dead. To map them into the game, we will be using a simple enum structure that we will be calling player state. Let's create a variable and export it, that we will be calling current state and that is initialized to the idle state. Let's also create another variable called previous state, just to keep a reference on the previous state in case we need it, although in the implementation in this episode we will not yet need it. Let's initialize it with null. Now, let's create the basic function that will execute each of the functions associated with each state. So, after the physics process function creates a new function and name it execute state. Inside, let's add the mock statement for the current state, and let's add each of the conditions for each of the states with a pass statement. Finally, let's call the function change state that will check if we can change the state and what should be the new one. Be careful in this step. After having recorded it, we have seen that we have misspelled in some cases the state word. We will be adjusting it later on as we find the different errors. Next, define the change state function. Again, add a match statement for the current state by copying it from the previous function. At the top of the function, let's save in the previous state the value of the current state. Now, let's start modeling the existing code into the new state machine. Go to the physics process and let's cut the code associated with the inputs readings. We are moving this step into their function that we will name handle inputs. Let's save the inputs readings in 4 variables: left, right, jump, attack. And let's define them at the beginning of the player script. We need to define also the button attack because in the previous implementation we were directly getting the key X. So, let's go to the project settings. From there, click on the Input Maps tab. In the action bar, type attack and then click on the button Add. We will have now an entry named attack. Click on the add sign at the end of the row, and click on the key X when prompted. Click OK to close. Let's start implementing the states. We are going to start with the idle state, which is the simplest. There is only to run the animation idle and to set the movement X to 0 as we don't want to move. Next, let's model the walk state. So, if the variable left is true, this means that the key has been pressed and we are moving to the left. Let's start by playing the animation walk. Adjust the movement X speed by adding the -max speed. Flip the character to the left by changing the flip horizontal value to true in the animated sprite. Let's copy the code and paste it in continuation of the walk state. Replace the left variable with the right, and adjust the max speed to be positive and the flip to be false. Next, time to implement the jump, which is also very easy. If the player is on the floor, then let's apply a negative speed in the y-axis through the variable jump speed. Since we don't have a jump animation yet, we will continue playing the one that will be running. Let's go to the hurt state, and let's play the hit animation. Since we want also to have some slight knockback, let's adjust the movement X to be slightly negative and the movement Y to be slightly positive. This will push the player back and upwards. We will adjust the values later when testing the function. We will leave the attack and dead states for later. Let's address now changing states, so let's move to the function change state, and again let's start with the idle state. So, if we are in idle and the left or right keys are pressed, we want to switch to the walk state. We can also change to the attack state if we are attacking. And to the jump state with the jump key that has been pressed. and add all the states that we can move from idle. Let's see now the walk state. So, if the left and right keys are not being pressed, we are not moving the character, and there, so it should move the idle state. While walking, we can attack, which means that if the attack key is pressed, we should also move into the attack state. In the jump state, we will only allow the player to move to the idle state when it is on the floor again. So for now, we will not allow attacks in the air. Let's go to the physics process and let's simplify the function. First of all, delete the condition that is checking if the character is grounded, and then add the handle input function that will check on each frame if the player is handling any control. Afterward, let's call the execute state function that will allow us to start working with the states that we have been defining up to now. Let's run the game. And we can walk left and right without any problems. And if we stop, we go back to the idle animation. We can zoom when stopped, but we cannot jump while walking. This means that we have missed one transition from the walk state to the jump one. So, let's fix it. In the code, let's look for the walk exit state and let's add a new condition. If the jump is true and we are in the walk state, then the next state will be the jump. Run the game again. And? Great! We can jump easily from the walking and when idling. Time to deal with the hurt state. For clarity, we'll move the contents of the take damage to be directly in the match case associated with the stat hurt. Let's adjust the knockback on Y to 100. Let's go now to the change state, and let's add the exit conditions that will allow moving from any state to the hurt state. Let's define also the exit condition for the hurt state that will be going to the idle state. On second thought, let's move the life decrease back into the take damage function from the player. Let's go up to the start of the function and define also a new variable dead that will have the initial value of false. Go back to the hurt state, and where we are destroying the object, let's set the dead variable to true. And then, in the dead state, let's add the queue-free instruction. In the hurt exist condition, let's make the transition to the dead state if dead is true. Let's run the game and see what happens when the enemy skeleton attacks the player. Wow, the knockback effect is too strong. Let's try to adjust it. We can see also that the hit animation is not running and is being resetted. Let's go to the hurt state, and before playing the hit animation, let's set it is not yet being played. Let's try it again. Seems to be working, but the knockback is still too strong. Let's keep fine-tuning it. In the walk state, we are calling several times to play the walk animation. Let's aggregate everything in just a couple of instructions. Let's run the game. Everything seems to be running correctly, but there is something wrong with the transitions in the walk state. Let's check it quickly. Okay. We have the wrong logical condition. Instead of a logical and we should have used a logical or, we want the condition to be false if either left or right are pressed. Let's run it again. And everything seems to be okay. To make sure that all the states are running correctly, especially later on if we add more states, let's implement a state debug. For that, let's go to the game scene, and let's add a new node to the player. In the search box, type label and choose the label node, that will the one that we'll be using to display the different states. Click on Create to finish and create the node. Move the label node to be above the head of the player and let's reduce somewhat the size. Let's go to the player script at the top of the script. Add a new onReady variable that will get the result of getNode with the name of the label that we have just created. This allows us to access the object and its properties and methods. For each of the states, let's add a new instruction where we set the label text to the name of our actual state. Let's run the game. We can see that now the state where the player is currently in, is correctly displayed in the debug text. To finish this tutorial, let's finally implement the attack function. In the execute state function, let's call the attack function. In the change state function, if the player is no longer attacking, then set the next state to be idle. To show how easy we can now add new features, let's add a small dash forward when attacking. So, when attacking, let's add a small movement into the x-axis by adding to the movement x50. Run the game. We can see that the player is moving, but always in the same direction. We need to adjust the dash with the current direction where the player is looking. We need also to flip the sprite. So, let's copy from the walk state the flip instruction and paste it in the dashboard. Let's check a last time to see if everything is as we were expected. And? It seems so. We have correctly set the basis for using finite state machines in our game. In the next episode, we will start to look at the user interface for the game to show the life level and the current score for the game. We will also expand on the level and start to generate some interactive elements like power-ups and platforms. We hope that you have liked this video. If it has been the case, consider subscribing, giving a like, and clicking on the notification button. If you have any questions, problems, or comments, don't hesitate in putting a comment and we will answer as fast as we could. See you in the next video, game developers.